Good morning, Chem 1. I already know what you're thinking. You're probably thinking, why are we starting a new unit? We're supposed to be ending. That is true. We are not going to get through all of Unit 13. We are just going to get through a few days. We'll have a quiz, and that'll be the end of the school year. We will go. We'll probably that quiz will probably land on Monday next week. So we're probably about a week away from being done. At least that's my plan as of when I'm recording this video. So we might try to get a class gathering like third period, fourth period. I might even tie a little extra credit to it for showing up, just because I selfishly want to see you all one more time. But that might be a way to kind of boost your grade here at the end of the quarter. So, Unit 13 is about solutions, and it's about mixing things together and what makes a solution, how we do that, what changes when we mix in different solutes into different solvents, and that's really what we're talking about. So let's go ahead and start here with Unit 13, 13.2. We're getting right into the notes. All right. Solutions are homogeneous mixtures. We learned this in first semester. What that means is the solute, when you mix it into a solvent, and you put salt in water, it will evenly distribute throughout the solvent. All right? The solute is the substance being dissolved, and the solvent is what's doing the dissolving. And usually, not always, but in chemistry, the solvent is typically water. I know this is a super wordy slide, but we're just going to kind of walk through it slow here. Most of the time, you guys think in terms of this, where solids are dissolving into a liquid, salt dissolving into water, sugar dissolving into water, and we call that soluble. But you can dissolve liquids into liquids, which would be they're miscible. So when you put alcohol and water together, they will mix, and so alcohol and water would be miscible. Now, there are things that are immiscible, like oil and water would be immiscible. They do not mix together because of their different polarities. We can dissolve gas into a liquid, that's soda, or there's dissolved oxygen like pond water. All right, typically, if they're not kept under pressure, those gas particles will effervesce. So when you open a soda, some of that carbonation comes out. We can dissolve liquids into a gas. That's like a perfume or an aerosol, something that we've condensed under pressure, and therefore when you spray it, it will go to a gas phase. And then gas is dissolved into gas. That's air. Air is N2, O2, H2, some helium, some trace noble gases. That's a solution of gases. Baking smells would be another example, and eventually those baking smells would dissipate because they spread and they mix and they spread evenly. That's diffusion. A solid dissolving a solid. That sounds like what? How does that work? Well, it only works if you get it really hot, and those would be alloys like metals. So stainless steel is a solid dissolved in a solid. Iron, chromium, nickel, some other things dissolve together because we melt them down, and then we resolidify and we've made a metal solution. All right, it's just in the state of a solid at that point. Solvation, or dissolution in water, is the process of basically dissolving things in water. You get two words here, dissolve and disassociate. Dissolves means is surrounded by solvent particles. So a dissolve would be like if I have a salt particle like Na plus here, and then water molecules would be all around it. Okay, that's dissolving it. But disassociating talks about the solute and how it breaks apart. So if I have an NaCl cube, salt cube, when we put it in water, it disassociates into its two ions, Na plus and Cl negative. So there's two different words. They're very similar, but it's really talking about what's happening with the solute and the ions in the solute, or not ions, depending on what we're dealing with, and what's happening with the solvent. So now we're going to kind of walk through a couple, like how ionic things behave in water and so on. Ionic things typically disassociate into their ions when they dissolve. So bonds are being broken. You have ionic bonds, an Na plus and a Cl minus, and you're breaking that bond when it dissolves. Okay, they disassociate. So it is dissolving in water, and the ions disassociate. They break apart from one another. All right, and that's kind of what this graphic here in your notes is showing, is those NaCl. So this is an anion being surrounded by water molecules, and here's the cation being surrounded by water molecules. Molecular compounds, all right, remember, ionic compounds are repeating patterns, NaCl, 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 and they're crystal structures. But molecular compounds are not. They're simply like CO2, for instance. This is carbon dioxide, and it's being put and surrounded by water, but that CO2 isn't going to break into its parts. Molecular particles do not dissociate. Okay, they stay, CO2 stays as CO2. It doesn't break apart into the carbon and the oxygen. Nope, CO2 bonded together by covalent bonds is going to stay. What we're breaking apart is the intermolecular forces that are holding CO2 together. In this case would be LDFs. So molecules will stay whole in water. One thing that we pay attention to, and when we're looking at solutions, is something called the heat of solution. It is the energy required to release when a substance dissolves. You may not know this, but and I would be able to show you this if we were in school, but when you dissolve different substances, sometimes the temperature will drop, and sometimes the temperature goes up. Some things dissolve and they get hot, some things dissolve and they get cold. And you might say, well, like, I've never noticed that when I put some salt in water, and that's because you put a really small amount of salt in a large amount of water. When we do this in school, I'd use a really small amount of solvent, water, and a lot of salt, and so you can actually feel the heat with your hands. If solute particles, there's kind of 3 steps to this solvation process. The first thing that needs to happen is solute particles must be separated from each other. The second step is solvent particles, in most cases water, they must basically be spread out so that the solute particles can kind of fit in between them. And then finally, the solute and solvent particles must attract to each other, right? They must kind of form a intermolecular attraction to one another. So the first 2 problems are more of a breaking, not necessarily bonds, but maybe intermolecular forces. When you have a breaking, that's endothermic. It's going to take energy to break things apart. And then exothermic, okay, then the last step is things coming back together. So we break the solute, break the solvent, and then we build them back together and rearrange them. And then, so you could call this building, okay? When we build, that's typically exothermic. That's going to release heat. So if it's endothermic, think about this, it takes heat, and then the change of H is positive because it's taking on heat, it's gaining heat. In the last step, the exothermic process, the change in H is negative. It's losing heat, okay? It's giving away heat, and therefore the amount of heat is going down within the system. The sum of these 3 steps is measured in joules. All right, we won't be walking through those 3 steps or making you calculate those 3 steps, but it's just good to understand there's like, when you dissolve salt in water, there's 3 steps that are occurring there. And so this is a graphic that you have that's kind of showing it. So here's our solvent, here's our solute. We got to break those apart first, which is going to take heat. And then they're going to mix together, and they're going to kind of reorganize, which is going to release heat. All right, that's what this chart is showing. The sum of the 3 steps is called the heat of solution, and that can be positive or negative, and therefore give us a hot, warm to the touch solution or a cold to the touch solution. If the sum of all 3 steps is endothermic, or positive, in other words, overall it gains heat, we would call that endothermic, and we would feel it as hot. If the sum of these is negative, we would say that that's exothermic, which means it's overall it's losing heat, and you're going to feel that as cold because the temperature is going to drop. And this is another example of this where the overall heat goes down. So we add our solute, they go up, and then the overall heat went down. Okay, so this would be an exothermic solution because at the end we started with, sorry, I'm pointing at the screen, you can't see me doing that. We started here at this heat level, and we ended way down here. So heat overall went down. So exothermic heat was lost overall. So a lot of times when we talk to you guys about heat equations, we try to simplify things. But you got to understand, we live in a world where chemicals and chemistry is constantly happening and multiple parts are colliding. And you can't just say like, oh, we're boiling water, heat's going into, right? in this scenario, we're starting to add more parts and lots of things are taking place together at the same time. The last thing we're going to go over here is the idea of solubility and the factors that influence solubility. Solubility is just how much solute can fit into a solvent. And it can be changed with different factors. At some point, the solvent will become full and you will not be able to add any more into it. So for instance, carbon dioxide. You can only put so much carbon dioxide into water to make carbonated water before it is full. There's no more space in between the water molecules. So there's three ways to think about this: unsaturated, saturated, and supersaturated. Unsaturated means we have less than the maximum amount. That means we can add more. So if we're talking about salt and water, unsaturated would be we can still add more salt, we can still dissolve more salt. Saturated would be at the maximum point. In other words, you've added so much salt and you're stirring it, it will not dissolve anymore, and that salt's just going to settle on the bottom. There's no more spaces between those water molecules. And then supersaturated, I'll post a video for this. You might have seen these hand warmers that are supersaturated solutions. They're sodium acetate. And what they do is they heat up the solution. They dissolve as much as they can at that higher temperature because hotter things can dissolve more. We'll get to that. And then they slowly cool it down and not disturb it. Okay, you might have seen this it's a hand warmer that you boil, and so you're heating it up so it dissolves, and then you leave it, let it cool very slowly. And as it cools, basically more solute stays dissolved than should stay dissolved. And then when you disturb it, you have a little clicker in the hand warmer. When you disturb it, it recrystallizes and comes out of solution. All right, I'll post a video, but basically a supersaturated solution has more solute than you should be able to hold at that temperature. And we can make solubility curves based on this. So a solubility curve, I'm gonna just show you the large version here. As you notice, as temperature increases, most of these lines go like this. Well, now what that means is these chemicals at a higher temperature can hold more solute. So let's take one that's not so busy here. Let's take KNO3. So at 70 degrees, KNO3 can hold, or is saturated, at a little, like 135 grams of solute. But if we cooled it down to 40 degrees, we'd only be able to hold, oop, I went too far. We'd only be able to hold like 65 degrees. So you can see that typically, as we heat things up, you can dissolve more solute. Why? Because you have more molecular movement and more space in between the molecules of the solvent, right? And that makes sense. If you want to dissolve sugar in water, if you want it to go faster, what do? You put it on the stove, you heat it up, okay, and it'll dissolve faster. You will notice that there are some of these lines going the opposite direction, meaning that as temperature goes up, we can dissolve less. Why would that be happening? It's because those are gases. Gases are the opposite. If you heat up a gas that's in solution, the solvent will hold less, and this makes sense too. If you heat up soda, what happens? It loses all its fizz. All the CO2 leaves when you heat up soda. So dissolving solids, more heat, faster solubility. Dissolving gases, more heat, less solubility. Okay, and use those logic like, okay, I know that if I heat it up, it'll dissolve more salt or faster. And if I heat up soda, the CO2 comes out of solution. Pressure can also affect how solutes dissolve. Solids and liquids, pressure does not affect them, and it's because solids and liquids don't compress. So like if I put pressure over top of water and try to dissolve salt, it's not going to make any difference. But gases do compress, meaning that if I add pressure to a solution, gases will be more soluble. This is why we put soda in sealed containers, because we're maintaining a pressure atmosphere so that the gas will stay dissolved. If we didn't do this, you know what happens to soda when it's not under pressure. It goes flat. The CO2 effervesces and leaves over time. Another thing that can affect solubility, so we got temperature and pressure for gases, is surface area. Typically, the higher the surface area, the larger the particle size, the faster things are going to dissolve. This is also something you understand. a sugar cube, we have different kinds of sugar. We have sugar cubes, granulated sugar, and then powdered sugar. Well, guess which one dissolves fastest? Powdered sugar, because you've taken it and made all the surface area around those molecules exposed. Okay, when it's in a cube, you only have the sides of the cube exposed, and there's internal sugar that's not getting exposed to the solvent. All right, so if we were going to rank these 4 seltzer tablets in terms of rate of solution, this guy here is going to be the slowest. Why? Because he has the least amount of surface area in contact with the solvent when you drop it in. Which one's going to be the fastest? The powder, because it has the most amount, fastest. Okay, it has the most amount of surface area exposed. Right, the other 2 would fit in there along in the same line, of course. And a 4th way we can change the rate of solubility is agitation or stirring. This is something you understand too. When you want something to dissolve, what do? You can shake it in a test tube. You can stir it with a stir rod. This is going to increase the solute-solvent contact and speed the reaction, the solubility reaction along. Okay? And obviously we need to take into account polarity. Like dissolves like. Remember that. Polar things dissolve polar things, and nonpolar things dissolve nonpolar things. This is why to get nonpolar paint off your fingernails, you use a nonpolar solvent, acetone. You wouldn't want water to dissolve the paint on your fingernails, or every time you wash your hands, your pretty nails would go bye-bye. Okay? So acetone will take off paint, which are both nonpolar, and water will dissolve most other things, like salt and sugar is a little polar. Okay, not much. If the polarities don't match, you're going to make a suspension. This is like oil and water. Oil is on top of water. Yes, it's a density issue, but the reason they're not miscible, the reason they don't mix together is because of the differing polarities. This is a graphic at the end of your notes that kind of shows that. This is like dissolves like here. Okay, so you have ethanol, which is polar, and water, which is polar, and so they're going to mix together, and the positives and negatives are going to line up. But hexane is nonpolar, and water is polar, and in this case, you might get some crossing the barrier, but they're not going to mix together as well. And you have to understand, as molecules get larger and larger, they might have like a polar end and a nonpolar end, and so they might mix together sort of, but not real well. Like dissolves like. Okay, you've probably heard that before, so just remember that for the purposes of this section. I know we went through a lot there fast. There is some math coming in this section, real simple, not difficult, but that's kind of where we're at. We're almost done. Just talking about solutions, and we'll be out of here in no time. Office hours are still in effect. If you need to come talk to me, need to come retake a quiz, or you want to retake a quiz and come tell me which one you need to retake, everything is not due to the end of the quarter. Anything that you've missed, you can still do it. All right? Anything you want to redo, come talk to me. Okay? I'm extending as much grace as I can. All right? As long as you put in the effort, you'll be fine. Have a good day. We will see you soon. Be good to somebody today. See you soon.